All right, so we are going to be working on the problem that we left off on yesterday, which was the uh, page problem, right? Where they wanted you to figure out the the size of the paper so that you use the least amount of paper and still fit 24 square inches of print inside of it. So yesterday we created our two equations of xy equals to 24, right? That was one of the equations. The other one was area equals to y plus 2 times x plus 3. So we had those two equations. We figured that we had to optimize the paper. Now the xy equals to 24 is a formula for the printed portion, right? So this would have been the printed part, okay? And the a equal to y plus 2 times x plus 3, this is the whole page. Okay, so we have to understand that those two equations, one is for one piece, one is for the other. They wanted us to figure out how to use the least amount of paper. So the whole piece of paper. So we're going to optimize the area on the right side, the whole page, right? So we figured that we couldn't take a derivative of it because there's an a, x, and y. So we substituted x equal to 24 over y into that equation. And we ended up with this equation right there after we substituted everything and worked it all out. Okay. At that point, we took a derivative. I told you guys to simplify, rewrite your denominator as a power that's negative. That way you can have an easier time doing it. We took a derivative and we simplified, and then we set it equal to 0. Okay, so this is where we stopped, and I told you guys bell was going to ring, so I said go ahead and solve it, try to figure out your dimensions. Okay, so what I would do from this point, okay, so starting from this point is I would write 3 equals to 48 over y squared. Okay, so I'd move that over. I get the y squared and multiply it, so 3y squared equals 48. I divide by 3, so y squared is equal to 16. So y is either equal to positive or negative 4, but it doesn't make sense that a length would be negative 4 units, right? So y must be equal to 4. Well, if y is equal to 4, then what's x equal to? Well, the way we do that one is we say, I know I had a formula that was xy equals 24. So if y is 4, then that means 4x is equal to 24. Or x is 6. Now I told you guys the answer was 9 by 6, right? And 6 by 4 is not 9 by 6. But the reason why we have those is because that's the dimensions of the printed part. That's what's going to optimize your printed part. So if you're going to print 24 square inches, you should make it 6 by 4. Okay, based on the information they wanted us to do with the 1.5 top and bottom and 1 left and right margins, right? So now that I know that, then according to the whole paper, okay, the whole paper, by looking at this picture, the width of my whole paper is supposed to be x plus 3. And the height of my whole paper is supposed to be y plus 2. Right? That's right here. So y plus 2, x plus 3. So to figure out my distances, or my lengths, then I'm just going to say x plus 3. Well, that's 6 plus 3. So that's 9. So the width of my whole page should be a 9, right? 9 inches. My height should be a y plus 2, which would be 4 plus 2, which gives me 6 inches. So the dimensions of the whole page should be 9 inches by 6 inches to use the least amount of paper. Now, a lot of times people say, like, how do I know I used the least amount of paper? Well, remember, we optimized it by taking a derivative and setting it equal to 0, which normally finds us the highest or lowest amount, right? Highest for how much paper you could use would be infinite, right? So it only makes sense that what we're solving for is the minimum. It doesn't make sense that we solve for the maximum, because the maximum amount of paper you can use is an infinite amount of paper, right? You can just keep making the page bigger and bigger and bigger. So there is no maximum to the size of the paper. You can always fit a 6x4 piece into it, no matter how big it gets, right? But you can't make it too small, because it still has restrictions that it has to be 6x4. And the margins still have to have a 1.5 inch from top and bottom, and then a 1 inch on the left and the right. So what we have to figure is, when we take our derivative, we must be minimizing, because maximization doesn't make sense for this problem, right? A paper can always be bigger, right? But it can't get too small. So that's what we did. We basically optimized it to be small. Okay? So those would be the dimensions of the whole page. Any questions on this? Need me to explain anything? All right, so the next problem we do is, I would say it's a tough one. Okay? If you thought these were tough, these are a little bit tougher. You tend to see these a lot on these exams for calculus. So let me write this one out for you guys. So example number 1. What is this? Number 3? Number 3. It says 2 posts, one 12 feet high and one 28 feet high, stand 30 feet apart. Okay, so 2 posts stand 30 feet apart. They are to be stayed. Now, the word stayed kind of means like they're going to stake them into the ground with a wire. Okay, so they're going to be stayed by 2 wires. Attached to a single stake. Running from ground level to the top of the posts. Running from ground level to the top of the posts. Where should the stake be placed to use the least amount of wire? To use the least amount of wire. So I'm going to pause this real quick just to give you guys a little bit of time to write down. All right, so the picture here. Let's make a 12 foot, and we'll make one that's 28 foot. Okay, so a 12 foot, 28 foot post. They say that they are 30 feet apart. So two posts, one 12 and the other 28, stand 30 feet apart. They are to be stayed by two wires attached to a single stake. So let's put the stake right here. Let's say that's where we hammer it in. And they're going to get wires and attach them to that stake. Now notice, they can put the stake anywhere. Okay, they can put the stake really, really close to the 28-foot one. By the way, let me write that down. This is 28 feet. This is 12 feet. But they could put the stake like right here and then just go straight up like that. Right? Or maybe they do it like this. Right? That could work too. I mean, it is that situation, a stake in between that's holding two posts with wires. I mean, it could look like this, maybe just a little bit further out instead of where I put it. How many different opportunities can I change the position of that stake? I mean, there's an infinite number of possibilities, right? So yeah, there's an infinite number of possibilities. So what we're about to do is figure out where's the best place to put it. Because for every position that I move that stake, it's going to require more wire on the left or more wire on the right. Okay? So just because you figure out, oh, here's one length, it's not going to fit everything. Right? So let's go ahead and try to figure out how we're going to write this stuff out. Okay? Now, if the whole distance here is 30, I'm going to label one of these triangles with an X. Okay? So let's call this X right there. So if that distance is X, what's the distance on the left side? This distance right here. You know, the whole distance is 30, and I marked that other side X. 30 minus X. Right? That would be 30 minus X. Because if X is 10, that means the other side is 20. If X is 20, then the other side is 10. Right? It has to change equally. So, all right. So we know that's 30 minus X. Let's call this Y. And we'll call this Z. So I'm just tying some stuff in because Y plus Z would be what? What would Y plus Z represent? The amount of the wire. So why don't we create a formula here for the wire? The wire is Y plus Z. Is everybody okay so far? So I'm just defining variables because Y is going to change over time and Z is going to change over time if I start changing the position of that stake, right? So it matters what X is, and then once I know what X is, Z is going to change, Y is going to change, and the 30 minus X is going to change, right? Everything's going to change. So it's important I can figure out what that value of X is. So let's write some formulas for the first triangle and the second triangle. Okay, let's see, because my whole purpose is to optimize the wire, correct? Least amount of wire. That's what they're saying. We want the least amount of wire. So I'm optimizing W, but I can't take a derivative of W because there's too many variables. Okay, so I need to somehow figure out how to get rid of either Y or Z or both or something to create something that's in common. So let's write up some formulas here. We'll start off with the easier triangle. X squared plus 28 squared equals Z squared. Okay, and then notice I have a z on that wire formula. So why don't I solve for z? No, I know it has an x in there, but if I solve for z, maybe I'll have an x in the w formula, and then I can maybe solve for y in the other one and have a bunch of x's in there too, right? So according to this, if I take a square root, of course it's plus or minus, but I don't need the negative because the distance can't be negative. This will be the square root of x squared plus 784. There's z. Okay? If I plug that into my w, then I still end up with three variables, right? I have an x, a y, and a w if I plug it in. So that's not really helping. But let me get the other triangle. That'll be 30 minus x squared plus 12 squared is equal to y squared. Now, if I take a square root of that, I get the square root of 30 minus x squared plus 144 equals to y. Now, I will simplify that. Okay, let's simplify that a little bit. So this will be, I'm going to expand 30 minus x squared, that's 900, minus 60x plus x squared plus 144 is equal to y. So 1044 minus 60x plus x squared is equal to y. Or if you want to put the x squared in the front, which I'm probably going to do in my next step. But notice how when I solve for y, I have x's. When I solve for z, I have x's. So if I replace my y and my z in my w equation, that sounds interesting, right? If I get my wire equation and replace y and z, then how many variables am I really dealing with? Just two. A w, which is my wire equation, and x's. So far, are we okay? I'm just trying to create equations to relate these things together. That's what I mean. This is still like related rates. We're just not moving anything, right? Nothing is in motion. So let's go back to w. W will be the square root of x squared plus 784 plus the square root of x squared, let me put the x squared first, minus 60x plus 1044. All right, who wants to come up to the board and take that derivative? Anybody? No? Don't worry about it. You don't have to do it. I'll do it for you guys, okay? So it's gonna be a bit messy, okay? So just kind of just hang on for the ride, okay? So let's see. What do we have? Now, before I do this, you guys understand why I'm going to take a derivative of w, right? We're trying to optimize the wire. That equation is the equation for the length of the wire based on my x position. Okay, that's why I'm going to take a derivative of w. It's not because I saw it and I'm like, yay, let's do it, right? I'd rather not do this, but that's what it is. The equation is what it is. So here we go. dw d what? X. By the way, you notice we haven't done d dt of anything, right? For related rates. That's a related rate thing. We haven't done d dt. Could you get a d dt type of derivative? Sure, if the variable happens to be a t variable, but it doesn't necessarily mean it's time. Okay? So, the derivative of this is x squared plus 784 to the half power. So I'm going to write half times x squared plus 784 to the negative half. So I'm going to write it down here, okay? I'm going to try to save a little bit of time. That's the x squared plus 784 to the negative half power that I'm supposed to get, right? But a negative half means bring it down, so I brought it down. And then the derivative of the inside is a 2x. You'll notice these will cancel out, okay? Plus, now the next part, x squared minus 60x plus 1044 to the half power. If I take a derivative, it's going to be a half times. It's going to be x squared minus 60x plus 1044 to the negative half. So bring this down. X squared minus 60x plus 1044. And now the derivative of the inside would be 2x minus 60. But the half will actually cancel stuff out on top. So let me rewrite this. dw dx is equal to x over square root x squared plus 784 plus x minus 30 over x squared minus 60x plus 1044. All right. So go ahead and write that down. All right, so what we're going to do is we're going to go to Desmos, and we're going to type this out, which I already did. So let me show you guys the formula. It's typed out for us right there. Look for where it crosses the x-axis. I already marked it for you, 21, 0. So that's our solution. So let's go back to this thing here. Let me get rid of my keypad. So I'm going to write dw dx equals 0 when x equals 21. Okay? So, now that we know that x has to be 21, let me go back to this picture. All right? So that means that this has to be 21. What's the other side have to be? 30 minus 21, so it's 9. So let me write a sentence about this. Okay? Let's write a sentence about this. The wire must be stayed 9 feet away from the 12-foot post and 21 feet away from the 28-foot post. And that's your solution. Again, use the technology you're given. Okay? I do not want to take a derivative of that function and solve it for 0. That's insane. Okay? Granted, I know the bottoms are not going to ever become zeros, so I mean, but still, it's a lot of work. They won't give you a problem like this on the AP and say no calculators. Okay? They're not going to do that. If they give you something like this, they would say use your calculator for something like this. Okay? They want you to type it all out. Again, one of the main reasons why I want you guys to practice with your calculator, because you got to be able to put that big equation into your calculator correctly. You got to use parentheses to signify numerators, denominators, stuff like that. Okay? But it's important that you guys learn to use them, because it's very hard to just pick it up, a week before and be like, okay, I got one. Hopefully I can do well on my AP. You got to have a little bit of practice time with it. Okay? So, any questions on this one? I know we started off with a bunch of variables, right? X, Y, Z, W, right? But they were all necessary because we had to kind of create a relationship between the wires on both sides. But yeah, you see this around the neighborhoods. Okay, you do see things, staked into the ground. Granted, they're not using like normal wooden stakes. They are using cement blocks to stake stuff into, so they're making sure it's on something that's not going to move anymore. But yeah, that's the way they keep these posts standing. Because if you don't have those stakes, those posts would basically collapse. Because most of those posts are holding more wires down the line and more posts. So they need that extra tension to help them stay up. Okay? And now that I mentioned the word tension, that's a physics problem. Because then they could ask you, okay, well, how much tension can these wires support? And how much tension are on these wires? Right? Because maybe the wires need to be thicker. Maybe they need to be thinner to save money, right? Maybe I don't want to use the wires that we normally use because they're just going to break. That's going to cost us money to replace them. So maybe we spend a little bit extra wire for a thicker wire. A little bit more money for a thicker wire. So maybe the cost is more expensive now, but the payoff is we save money in the end, right? So this is how real world situations occur. And this is done daily. This isn't just like, oh, there's a computer program that can do this for us. Yes, there are, but I was talking to one of my students earlier during first when I was helping them. We have computers that do a lot of these calculations for us, but you still need people that know how to program those things, right? We still need mathematicians that can tell the computer programmer, we need this equation in there, because that will do it, and this is how it's got to work, and this is how you're going to have to spit it out, right? Just because we have machines that can do it now doesn't mean that we just stop, right? We got to keep working at it, make it better, make it better. Because if once somebody figured out a calculator and said, oh, that's good enough, I don't need to make it better, right? You know what you guys would all be using right now? Not a calculator. You'd be using an abacus because that was the first calculator, okay? And it's a good calculator and it can do a lot of stuff. But if we stopped once we figured something out, then that's where you'd be stuck at right now. You'd have a big old abacus in front of you, just try to do calculations. And unfortunately, that does not graph. Right? It doesn't do any of this other stuff. So, yeah, you got to keep moving forward, right? All right. Let me see. I want to see if we have one more. I think I'm going to stop here.